Hello and welcome to lecture 44 of the course Computational Complexity. So today in this lecture we will see a connection between randomized algorithms and circuit complexity, right? So we will see this this language which we had briefly seen during when we talked about a randomized algorithm called polynomial identity testing, okay, and short PIT. So what is polynomial identity testing? We'll see that, and then we will see an application to of polynomial identity set testing to a problem of determining whether a given bipartite graph has a perfect matching, and then that would imply that that problem of determining whether a perfect bipartite graph has a perfect matching. This problem is in a class called randomized NC. Okay, right. So polynomial identity testing simply is asking if given two polynomials f and g, it's simply asking whether f and g are the same polynomial. Okay, so one may think, what is the big deal to just compare the two polynomials? The catch is that these two polynomials need not be given in the exact same format, right? If there is a standardized format, such as the leading term has the highest degree, then the second term has the second largest degree, or some standardized format, then it's just a matter of checking between the two. But then even the way the polynomials are specified itself could be in different ways, right? So this may require us to do some computation. So just to give an example, what if the polynomials are f and g are given like this: x minus 1 plus multiplied by x plus 3 multiplied by x minus 6, and like this, x cubed plus 4x squared minus 12x plus 18. This is g. So now how would you do this? So you can try to reduce the polynomials to the standard form, but on the first look both of these, the leading terms look like x cubed, so that seems to be same. The constant term here is plus 18 in the left hand side, and in the right hand side, in the right hand side is plus 18, in the left hand side it is minus 6 times plus 3 times minus 1, which is also plus 18. But then when you look at the coefficient of x squared, right, it will be just the sum of this minus 6 plus 3 minus 1, so it will be minus 4, whereas for g it is plus 4. So you see that these are not the same, right? So one approach is to standardize the polynomial and compare, and this can be done for univariate polynomials. So univariate means polynomials of a single variable, such as this. Here the only variable in f and g above is x, but if you have multiple variables, let's say the number of variables is n, then potentially you could have many such factors like x1 plus x2 multiplied by x3 plus x4 multiplied by x1 plus x6 multiplied by x1 plus x7, some lot of terms, and when you try to multiply them all, it could result in an exponentially large polynomial, right? So the given polynomial may be in a very crisp short format, but when you try to expand them, it could result in an exponentially long polynomial, and this will make our algorithm non-polynomial time. So this will lead to a not inefficient algorithm. So this is not something we want to do, right? So this problem for multivariate polynomials in particular can be hard, and in fact, as of now, right, as of today, we don't know an efficient algorithm for doing this problem, polynomial identity testing, when the input polynomials are multivariate. So when the input polynomials are single variable, then it is easy. You could just x minus 1 into x plus 3, you could just multiply them out, and this can be done efficiently, but not so in the case of multivariate polynomials. So let us try a very simple randomized algorithm. I think I touched upon this while discussing randomized algorithms myself, but still I will just quickly go through it. So choose a random number, okay, in place of x. So let us say we choose r from, and instead of saying choose a random number without any without specifying from where, let us say we choose a random number from a fixed set S. Okay, so this could be some, so let's say it is degree 10 polynomial. So S could be some set of size 1000, right? So you could say S is for example, right? For example, S S could be just the first 1000 natural numbers, right? So S could be anything. Now you, and from that S you randomly pick a number R. Now you evaluate the polynomial f, right? So it's one thing to simplify the polynomial, it's another thing to evaluate it. So now suppose R is let's say 10, right? So for G here you have 10 cubed plus 4 into 10 square minus 12 into 10 plus 18, right? So 1000 plus 400 minus 120 plus 18, you can compute that. For F it is just 10 minus 1 9, 10 plus 3 13, 10 minus 6 4. So 9 times 13 times 4, it's a product, right? So it's one thing to evaluate and one thing to expand without evaluating, right? So just evaluate the polynomials at R, both the polynomials, and then check whether they are the same. And if the evaluations happen to be the same, you say the polynomials are equal, right? And if the polynomials are identical, if the evaluations are different, then you say the polynomials are not identical, right? So this is the polynomial. This is a very simple, right, randomized algorithm. In fact, this is one thing that you will keep seeing whenever you encounter randomized algorithms. The algorithm that you see usually will be extremely simple to describe and program. But the proofs may be long. The proof of correctness or proof of running time, this could be long. But the algorithm itself is usually very simple. So how simpler could it have been, right? You have two polynomials that you want to determine whether they are identical. You just substitute random values and check whether they are the same. They evaluate to the same value. So now the correctness. Let's see the correctness. Suppose let's say when you evaluate the polynomial at 10, let's say, now f of 10 is different from g of 10. This necessarily means that the polynomials are different, because if the polynomial were the same, then you evaluate it at any x, they should give the same evaluation, right? So if f and g are the same, then at any point r, they will always give the correct same evaluation, and therefore if f and g are the same, you will always output the correct answer. We will always say it is identical. However, if f and g are not the same, right, in that case there is a small possibility that you may end up getting an r for which the polynomials could be different, but the r led you to saying that the r forced you to say that f and g are the same, even though they are different, right? So just as a simple example, maybe let's say if you have x squared and let's say x squared plus 10x, let's say x squared plus 2 and x squared plus 10x plus 2. Right? At x is equal to 0, these two polynomials are different, x squared plus 2 and x squared plus 10x plus 2. But at x is equal to 0, you see that they both evaluated 2. Right? So this is an example of a case. So which are the r for which f and so the point is that there may be r for which f and g get evaluated to the same value, and this is the only possibility of error. So even though the polynomials are the same, it could so happen that you pick an r for which they evaluate to the same value. So what is the probability of error? The probability of error happens only when f is not equal to g, or f and g are different polynomials. Right? When f and g are the same polynomial, there is no error. Right? But the error happens when f and g are not equal, but fr and gr are the same. And this happens when r is a root of the difference polynomial. Right? The difference is f minus g. So here what happened here? X squared plus 2 and x squared plus 10x plus 2, the difference is, so the difference is simply x squared cancels, 2 cancels, it's just simply the polynomial 10x. So here the choice x is equal to 0 happens to be a root of 10x, right? That's what happened here. And it could happen in different ways. So r is a root of f minus g. But we have what is called the fundamental theorem of algebra, which says that If a polynomial is of a certain degree, then let's say degree d, then it has at most d roots. Okay, so if f and g are of degree d, then the difference is also degree d, right? At most d, maybe even smaller, and in that case the difference has at most d roots, and you picked R from a big enough set, right? So if you recall, we picked R from a set of size 100D, right? So there were 100D values, and out of which you chose one value, and there are at most D roots. So not all of these D roots not all of these D roots may be present in the set S, but the maximum number of roots that can be present is all of them. So, and that is D of them. So, and we give the wrong output, you report the wrong answer if R happens to be one of these D roots or one of these roots. So, the probability of error is picking one of these D roots from the set of size 100 D. So, which is D divided by 100 D, which is at most 1 over 100. Of course, you could boost this probability of error, right? So, this is a very simple randomized algorithm that for the polynomial identity testing. But still, what I have described is still single variable case, and I already told you for single variable you could simplify the polynomial and then get the answer directly instead of all this substituting or evaluating at a certain point. For the multivariate case, so let me just say, so instead of using f and g, let me just use one polynomial p, because if f is the same as g, then the same as saying f minus g is equal to 0, right? So instead of that, we will just check whether a polynomial is identically equal to 0. Identically equal to 0 means the polynomial should be the 0 polynomial. Each monomial should have coefficient 0. So it is just a 0. The polynomial is itself 0, right? Not that it gets evaluated to 0 at some point, right? It's 0, right? It's everything is 0. Now, again, this may seem straightforward, but then we may have some strange ways of accessing, or the polynomial may not be given to us in a standard format. It may be given to us as a addition, multiplication, difference, everything, or it's also possible that it is given to us in some query format. So again, we could do the same kind of idea, right? So now the only difference is that we have n variables x1, x2 up to xn instead of one variable x. So similarly, now we pick not just one R, but R1, R2 for each of these x1, x2, etc. Right? So we pick R1, R2, etc. from S power n, okay, where S is of size 100D, the same set S, or same or similar sized set, right? So that is R1 is chosen from S, R2 is chosen from S, etc. at random, and then you evaluate the polynomial at these points R1, R2 up to Rn. If it outputs, if the polynomial at R1, R2 up to Rn evaluates to 0, then you declare that the polynomial is identically the 0 polynomial. Okay, maybe I'll just say one more line. If it evaluates to a non-zero value, then you declare polynomial is not identically 0. Okay, so the correctness is, I hope, fairly clear, or at least to the problem, with the exception of the error. If the polynomial is the 0 polynomial, then whatever R1, R2 you substitute will give you 0. So in that case, you will always output 0. The polynomial is 0. But even when the polynomial is not the 0 polynomial, there is a possibility of R1, R2, etc. being being chosen in such a way that, again, the choices are all random, but then you could happen to choose the R1, R2, etc. in such a way that the evaluation is equal to 0, right? So there is a probability of choosing of unluckily choosing the bad R1, R2, etc. which evaluates 0, even though the polynomial itself was not the zero polynomial. So you may incorrectly output that the polynomial is 0 when the polynomial is not 0. That is the only possibility of error. Okay. In the case of single variable, we were able to say something like this, right? We were able to say this: if f and g are of degree d, then there are at most d roots. In the case of multiple variables, can we say something like that? Sorry. Right. In the case of multiple variables, can we say it has at most d roots or something like that? Right. That is the question. If we can say that, then we are done. So we cannot exactly say that, but we can say something very similar, and that happens to be enough. So this is the Schwartz-Zippel lemma, or also sometimes called DeMillo-Lipton-Schwartz-Zippel lemma, which says that if the polynomial is not identically 0, right, which means it is not the 0 polynomial, and in this above setting where we choose S from a set of 100D, where D is the total degree of the polynomial, right, then the probability that you evaluate to 0, right, you pick R1, R2, and these R1, R2 evaluates the polynomial to 0, this is at most D divided by the size of S. Right. So this is exactly like what we wanted above. Right. So here we said the probability of error was D divided by the size of S, which was D divided by 100D, and again the same thing here. The probability of error is D divided by the size of S. Right. So the probability of error in this setting is 1 divided by 100. So if P is identically equal to 0, algorithm outputs correctly, and if P is not identically equal to the 0 polynomial, probability of error is at most 1 divided by 100. Right. So there is some probability of error, and this is at most 1 divided by 100. Okay, so this is the so strictly speaking, when you are looking for identity testing, meaning whether this is 0 or whether the polynomial is 0 or not, that's why it's called identity testing. Meaning identity means 0 is the identity polynomial, meaning it's additive identity, right? This is a co-RP algorithm when you look at it in that perspective. But if you want to, if you change the language around, if you are checking whether the polynomial is not identity, then it is an RP algorithm, right? So again, RP, co-RP or complement. If L is in RP, then L complement is in co-RP, right? So this is a RP algorithm. If you are looking at the question of, so this is an RP algorithm for the language, not for identity testing, for I'll just write down the language. Set of all P, let's say x1 up to xn, P is not identically 0. Right, so there is a small error in the case of it not being 0, and when in the case of it 0, it is outputting correctly. And this problem, it is this is kind of interesting, and the reason I'm saying this is because so we saw a simple RP or co-RP randomized algorithm, right? We still do not know an efficient deterministic polynomial time algorithm for this. In other words, is PIT in P? This is still open. So this is one question where randomized algorithm seems to help, right? We know of a efficient randomized algorithm, but we don't we don't know still whether there is a deterministic polynomial time algorithm. Okay, so this is one of those problems where this is the case. Now, I hope this explanation is clear. Now I will move to an application, the application of bipartite matching, and that will lead us to seeing that the problem of bipartite perfect matching is in the class RNC. So a bipartite graph is a graph where all the vertices can be classified into two groups, partitioned into two groups, and all the edges are cross edges going across. So like in the picture over here, A, B, C, D, E are on the left side, 1, 2, 3, 4, 5 are on the right side, and all the edges are going across. And you can write a adjacency matrix, right, where so the usual adjacency matrix writes all the vertices on one side and the number of rows and columns is equal to the number of vertices. But for bipartite graphs, for undirected bipartite graphs, even for undirected bipartite graphs, you could have a somewhat more you could compress the adjacency matrix into the following form because there are no cross edges. So what I mean is, the rows are indexed by A, B, C, D, E, and the columns are indexed by 1, 2, 3, 4, 5. And from A to 1 there is an edge, right? So for A to 1 there is this edge, and that is this one that I have circled, right? And from E to 1 there is another edge, and that is the edge I have circled here. Right. So like that you could see how this adjacency matrix relates to the graph given. Okay, so this is the adjacency matrix of the bipartite graph. So the question is there a perfect matching? What is a perfect matching? A perfect matching is a subset of the edges such that each vertex appears exactly once in the amongst the edges. So maybe I will just write that down also. Okay. Perfect matching. Any graph has a perfect matching, so I'll just say PM if there is M, which is a subset of edges, right? So maybe I'll just say G equal to VE. So V is a set of vertices and E is a set of edges. So if there is M, there is a subset of edges such that each V in V is the endpoint of exactly one edge in M. So each vertex must appear as the endpoint of exactly one edge in M. Okay, so this exactly is important. It is not at most, it's not at least, it's exactly one edge in M. And for the above graph, we have chosen a perfect matching here. So A appears once, B appears once, C appears once, E appears once, everything, and same for 1, 2, 3, 4, 5. And correspondingly, I have highlighted the ones in the adjacency matrix that corresponds to these edges. Right. So A5, right. So the E1 is this one, and A5 is this one, right, and the other ones you can see. Right. So this is a perfect matching, and this is we are asking whether the graph G has a perfect matching. Right. So, and if there is a perfect matching, what I am saying is that now if you look at the ones in the adjacency matrix, I will just erase this over here. If you look at the ones, you can see that every row has exactly 1 1, right? Every column has exactly 1 1. So there is no row that has 0 ones or more than 1 1, right? Every row and column has exactly 1 1, right? So G has a perfect matching if and only if there is we can choose a set of ones from the adjacency matrix. Choose a set of ones from the adjacency matrix such that every row and column has exactly 1 1 each. Okay. So now I could write the same thing. So this is what we will try to encode. Okay. So recall the idea is to show that perfect matching is in randomized NC. So we are trying to move towards that. So randomized NC is still a circuit class. Okay. So one way is to look at what is called the permanent. So permanent basically checks. So now you look at it. So for row 1, it is a fifth in this matrix. If you look at it, the row 1, it is a fifth entry, that is the fifth column. For row 2 is the second column, row 3 is the third column, row 4 is the fourth column, and for row 5 it is the first column. So each row is matched to something, each column is matched to something, right? So and all these entries should be 1. So there should be a rearrangement of the there should be a remapping of the rows, a mapping of the rows to the columns such that all the entries of the corresponding things are ones. So there should be a sigma such that the I comma sigma ith entry is 1 for all the I. There should be a permutation such that for all I there is a sigma ith column, so that the I comma sigma ith entry are all ones, right? So this is what we want to check. So we'll add. So there is a summation here over all the permutations sigma, such that if you take the product of all the entries ai sigma I, so once the sigma is fixed, you are just, so sigma could be the identity permutation. So if you take the identity permutation here, it will be 1 1 2 2 3 3 4 4 and 5 5, but that will be 1 times 1 times 1 times 1 times 0, right? So the identity permutation will give you the product 0. If you take some other permutation, let's say 1 comma 2, it will be this 1 2 comma 3 3 comma 4 4 comma 5 and 5 comma 1. Again, it will result in the 0 product because there is only 2 ones, right? But if you took the permutation that corresponds to the perfect matching, you will get 1 for the summation. So this perfect matching, the existence of the perfect matching corresponds to there being this quantity not being 0, and this quantity is actually a well-known quantity of a matrix called permanent. Okay, so again, this name is not important right now, but this is just the this is what is called the permanent, and we will see in the upcoming lectures or in the upcoming weeks that permanent is not something that is easy to compute. In fact, it has been shown that it is even more harder than like it's as hard as more harder than NP and things like that, right? More harder, or at least as hard as NP, right? So this quantity is called permanent, and it's not easy to compute, right? So we are taking for all the permutation of for all the rows, we are taking the permutations of the columns and checking whether they multiply to 1. So what is the permanent of this matrix? Actually, in fact, you can see that you can see this. So if you look at the term inside the summation, this term is either 1 or 0 for a 0 1 matrix, right? Because it's just a product, so it's either 1 or 0. The number of times this term will be non-zero, or the number of times this term will be 1, will exactly be the time will be exactly be the times when the permutation corresponds to a perfect matching. So it's the same as asking how many perfect matchings does this graph have, and you can check how many this has. I think E should map to 1 no matter what, and E mapping to 1 because that is the only edge of E. That would mean A cannot get 1, so A has to map to 5. Right. Okay, so the top graph is not the same as bottom graph because D does not have a partner in the bottom graph, the top graph. And once these two are fixed, A to 5 and B to E to 1, then B has to move to 2 and D has to go to 4. So this is the only one perfect matching that this graph has. And so for this particular graph, this permanent will actually be equal to 1. And in general, it will be equal to the number of perfect matchings. However, I said that this quantity is not easy to compute. So now what is the way out? In fact, there is a very related quantity to the permanent, quantity very similar to permanent that we are very familiar with. So if in addition to all of this, if we included like a sign here, sign meaning if we introduce a sign quantity here, then it becomes what we know, what is familiar to us as the determinant, so which is what I have written here. So this is exactly the same as permanent, but I have just introduced a sign. So sign is like plus or minus. It is just, so if the sigma is an odd permutation, it is -1. If sigma is an even permutation, it is +1. So it is just alternating the terms into plus and minus terms. And then it becomes very familiar to us. So if you recall the definition of determinant, it is just that 1 into the determinant of this submatrix, right, and then -0 into the determinant of the corresponding submatrix plus 0 into this, right. So there is a definition of the determinant like that. So this determinant is similar to permanent, but it has a signed quantity, right. And but then we know that determinant is easy to compute. It is kind of counterintuitive because the addition of sign actually we feel makes it plus and minus and makes it harder to compute. Whereas if the top one without the sign, it is just all additions, we would think that this is simpler to compute, right? It would seem that permanent is the easier one, but interestingly determinant is the easier one and permanent is the harder one. Okay, so this is the determinant. Right, so the determinant, but what we know is that suppose the permanent is equal to 0, which means all these products should be equal to 0, right? We are still dealing with a 0, 1 matrix. So all these terms will be either 1 or 0. So it's just an addition of a bunch of 1s. So if permanent is 0, then no matter what you put as sign, the determinant will also be 0, right? However, if permanent is non-zero, right? Maybe I just write over here. Permanent of A is 0 implies that determinant of A is equal to 0, right? Because all the individual terms must be 0. So in the case of when A is 0, 1, A is a 0, 1 matrix. However, permanent of A is not 0. This need not imply determinant of A is not 0. Meaning even if there are some, if the permanent is non-zero, it could so happen that this, because of the sign plus and minus, some terms could cancel and determinant could still be 0. So permanent, checking the, even though determinant is easier to compute, checking the determinant is not the correct thing, because there could be matching, which means permanent is non-zero, but then these matching could cancel with each other and resulting in determinant being 0. But if determinant is non-zero, we know for sure that permanent is non-zero, so we know for sure that there is matching. But if determinant is 0, it could either be because there is no matching or because there are matchings that cancelled with each other, right, because of the sign. So the sign creates this problem. So what we will do is we could use polynomial identity testing to check this, right. So the problem of cancellation comes when these are all plus 1, 0 and 1, right. So what we can do is to take the same matrix and replace the 0 ones with variables. So I replace the ones with variables and zeros be zeros. So this is the matrix 1 0 0 0 1 1 1 0 0 0. So now I am replacing each one of them with variables. So the first one is x11, the last one is x15, second row is x21 and x22 and so on. Right? So all the ones have been replaced with variables. Right? So they are all different variables, they don't have any relation to each other, right. So each one is replaced by this, zeros remain zeros. Now the claim is that as a polynomial, now these don't cancel, right, because each row and each column has different, whenever there is one, it's a different variable, so it cannot get cancelled. So even though they are opposing signs, you cannot get two terms to cancel with each other because the variables involved are different. So G has a perfect matching, right, this is the main point, if and only if the determinant of this matrix is non-zero. So the determinant is a polynomial, right, it's a polynomial in these variables. This determinant is not identically 0, meaning it is not the 0 polynomial. So just one more point, this matrix is called the Tutte matrix, T-U-T-T-E, after the graph theorist, and we use the symbol T to denote this, right. So we are asking whether this determinant is non-zero, is what we are asking here. If this determinant is 0 means determinant is non-zero means there is a perfect matching. If the determinant is 0, there is no perfect matching because there is no way that things could cancel. Determinant 0 means permanent of the adjacency matrix is also 0. And to test this, we could just use a polynomial identity testing, right? What we saw earlier, right? And so that is the algorithm, right? So we can use. So the graph has a perfect matching if and only if the polynomial is not identity, right, or not identically 0. So this gives actually an RP algorithm, because if the graph has a perfect matching, then the polynomial is not identically 0, and then your algorithm outputs correctly, right. Right, so it's asking, this is an RP algorithm for the polynomial for not identically 0. It's an RP algorithm. So now let us see why this implies. So we are talking about the problem of asking whether the graph has a perfect matching, right. So the language is decision version of whether the graph has a perfect matching, right. It's not asking. Okay, so we'll come to that in a bit. And this implies that this problem is in a class called randomized NC. And why is that? So before that, I'll just say one more point. So the class NC is usually considered to be the class of problems on which we could, for which there are efficient parallel algorithms, because we say NC is like bounded depth, right. So we could consider each gate as a different processor, and you have bounded depth, so you have n inputs, so presumably lot of each input is being processed by a different gate. So this can be thought of as a parallel processing, right. So the class NC is considered as the class of languages that have efficient. I think I mentioned this when we defined or got into circuit complexity at the beginning lecture of circuit complexity. Efficient parallel algorithms. Right. So here the point I want to make is that now the question of whether the graph has a perfect matching is reduced into computing the determinant of a certain matrix, right, of the third matrix. And what is the algorithm that we use to compute the determinant? We will use polynomial identity testing, and the algorithm that we described for polynomial identity testing was a randomized algorithm, right? Right. So we said that or a polynomial non-identity testing was a randomized algorithm. So it is actually a randomized algorithm. It's a computation of the determinant, but also using randomization, right? So the class randomized NC or randomized equivalent of NC, sometimes referred to as RNC, is the same as NC. In the sense of size and polylog depth, etc. But just that it also allows some random input bits. So some input bits are random, and in addition to the actual input. So there is random input and the actual input. Okay, so that is RNC. So it's exactly like NC, but there is scope for random inputs as well. And although I didn't mention it at that time, so we saw that matrix multiplication is in NC, and even determinant is actually in NC, right? So fact determinant can be computed in NC2. So log n squared size depth is enough. So if the graph has a perfect matching, then the determinant of this quantity is non-zero, and so determinant of t is not zero, which means that if determinant is t is not zero, then which means that with high probability we will accept. Right. So when will we accept? We'll accept whenever the polynomial identity testing algorithm, we'll put some random values for x11, x12, etc., and then evaluate the determinant of that matrix. And this is very likely to be non-zero if the input is non-zero, but there is a small chance that it becomes zero. So with high probability we will accept. If the graph does not have a perfect matching, right, then determinant t will be 0, which means whatever values you substitute, the determinant will still be 0. So we will, it's not high probability now, we will always reject. So this is, so I'll state the final result. So perfect matching, so I'll just define the class or the language. Perfect matching or maybe I'll call it bipartite perfect matching is a set of graphs G. G is a bipartite graph. G has a perfect matching. And what we showed now is that bipartite perfect matching is in RNC, because determinant computation is in NC, and then we have to accommodate randomness, because the algorithm that we have for polynomial identity testing is a randomized algorithm. So this is in RNC. So I'll quickly summarize and then say some conclusions. So the randomized algorithm for polynomial identity testing was fairly straightforward, just substituting some randomized algorithms. I stated the DeMillo-Lipton-Schwartz-Zippel Lemma, which says that the fundamental theorem of algebra generalizes in the multivariate setting also. So this is also an extremely interesting theorem, lemma, and has a very short proof. So if you're interested, you let me know. I'll share some references to this. It's very simple, very short, but just that we don't have time to get into the proof. I'll be happy to share references if you're interested. Okay. Then we saw the problem of bipartite matching. And then we saw that graph has a perfect matching if and only if the permanent of the adjacency matrix is non-zero. But permanent is a quantity that is not so easy to compute. So we went to the determinant, but then that leads to errors. So instead of actually checking whether the determinant is 0 or not, we check for the determinant of the TUT matrix, where each value is replaced by variables. So each one is replaced by variables, 0 remains zeros, and all we have to do is compute the determinant of this polynomial. So the matrix has variables, so the determinant will be a polynomial. Compute the determinant of this matrix, which will be a polynomial, and check whether it is not identically 0 or not. Right? So we know that in this matrix, graph has a perfect matching if and only if determinant is non-zero. This equivalent is exact. There is no error here. But checking for determinant equal to 0, identically 0, uses polynomial identity testing, and that gives us that a randomized or RNC algorithm for the bipartite perfect matching. 2 points, or maybe 3 points. So one question is, what about, so this is a decision problem, right? It tells us answers whether the graph has a perfect matching or not, right? What about now outputting a perfect matching, if there is one? If the graph has a perfect matching, can we output this perfect matching? And the answer is that this also can be done in the RNC. Perhaps we will see this in the next week's lectures. And 2 is let me just say, bipartite perfect matching, or is perfect matching in general is this in NC. So without use of randomization, can we get a parallel algorithm for perfect matching? And this is still unknown, this is still open. Whereas the first one, yes, you can do it. We will see it also. This is still unknown. There has been a lot of work. Even recently, even the last 5-6 years, there has been a lot of work where people have proved that for some special cases of graphs, perfect matching is in NC, right? For instance, and for planar graphs, right, perfect matching is in NC, but still the general question is open, right? So the general question is still open on this. And with that, we come to the end of week 8, right? So we saw most of week 8 was taken by the proof that parity is not in AC0, right, which was by the approximation we approximated each function, or an AC0 function. We could approximate it using a low degree polynomial in F3 over F3, and then we showed that parity cannot be approximated by a low degree polynomial over F3. Then we saw the result that BPP has polynomial size circuits. Any language in BPP has polynomial size circuits, which was just by noticing that every you can do the boosting enough number of times so that there is one random string that will be a witness for all the input strings of a certain length. And if you hard code that, you get a one circuit for all the inputs of a certain length, right? And without any randomness. This is Adelman's theorem. And then we saw today in this lecture, we saw the polynomial identity testing and how it applies to bipartite matching, and finally seeing that bipartite perfect matching in bipartite graphs, that it is in the randomized NC class. And that's all from me on week 8, and thank you.